Yeah.
Yeah, I'm here.
So what Douglas said is almost correct. There's one thing there.
Can you say it again, Doug?
I thought it was a binary tree. I think what it is, it's an unbalanced tree. Maybe that's where I mixed up. But
the question is it a binary tree, yes or no? And why? And what is the definition of a binary tree?
I had said, oh, is it just no more than 2? If it's no more than 2, I think we're still a binary tree.
That's
but
correct.
I thought it was it has to be 2, unless you're at the deepest level.
That's correct. That's correct. It is a binary tree because at most 2 nodes. If it doesn't have 2 nodes, that's fine. Okay, so we talked about a little bit on binary search when we saw trees. What do you guys remember about that? A binary search, and more specifically, a binary search tree.
It's like a dictionary.
In what sense? Like, if you could expand on that.
Sure. So like when you go through a dictionary, the easiest way to go through it is kind of like just open it and then see if the word that you're looking for is to the left or to the right. And in this case, what numbers would be if the number is greater than the root or less than the root. And you search that way.
That's correct. Searching like a phone book or a dictionary. Or a word dictionary. There is dictionary. Some people call, in other programming languages, an object, they also call it a dictionary. I'm not sure if we had talked about that. Or a hash table, they also call it a dictionary. So that's why I'm specifying here word dictionary.
Okay, yeah. Yeah, I have heard that before. So that makes sense that they could be confused.
Yeah, just have that in mind whenever like somebody asks you to store something in a dictionary, they mean an object, a hash map, etc.
Okay.
Okay, so if we're asked to find the number 7 in this object in this tree, could you describe what you were saying, Peter, again?
Sure. So you said the number 7?
Yeah, let's say we want to find if 7 is in the tree.
Okay. So you would look at the root, and in this case, our root is 8. So then you would say, is 7 greater than or less than 8? And because 7 is less than 8, you want to go to the left.
Okay.
And then you'd be at 3, and you would look, and you'd say, is it greater or less than 3? And then you'd look at, it's greater than 3, so you'd go to the right of 3's children. And then you would do the same thing with 6, and you would just keep doing that until you got to the number you were looking for.
You would just keep doing that until you got to the number you were looking for. So that simply put is binary search, where we are getting rid of, you can see we're getting rid of roughly half the problem by looking at the current node, seeing if it's less than or greater than, and deciding based on that what half do we search, basically. You can see that this tree has 1, 2, 3, 4, 5, 6, 7, 8, 9 nodes, and on the first try we already eliminated these 4. On the first test we already eliminated 4, and on the second test, which is when we're on 3, because this is not full with other nodes, but if it was, we will be also eliminated half of the problem there. And so on. Okay, so this is basically binary search, and now what we'll learn today is how to implement this in an array, which is the same algorithm, is the same idea, just the implementation changes and the data structure in which we're applying this algorithm changes. Okay. but I actually want to share an introduction that I really like to binary search, and is by this guy. Wait, no, not that link. Some of you might have seen this already. This is the CS50 from Harvard, the computer science class from Harvard. Oh, I thought I had. Hold on. The link might not be. I had a link that had the time. This one is the one. And if you haven't seen it, I'd highly recommend it. It has like a lot of general concepts that are valid for what we do. Let me know if you can hear the audio, or actually, let me just make sure that you can hear the audio. Share computer sound. Share. So let's make this full screen.
That's what's inside this so-called black box. And this is where computer science comes in. An algorithm. Anyone know what this term is? What's an algorithm? You sort of read about it all the time these days, especially in the context of self-driving cars and Siri and Alexa and so forth. Yeah. A set way to do something. Yeah, and in the context of problem solving, an algorithm is just step-by-step instructions for solving some problem. So what might an algorithm be for a problem that we might want to solve? Well, consider this. This is an old school problem where you might have lots and lots of names and lots of numbers, and those names are hopefully sorted alphabetically from A through Z in a book like this. And even though most of us don't really reach for this technology anymore, consider that it's really the same as your iPhone or Android phone or other device, which has all of your contacts top to bottom, and you can scroll through them from A to Z, or you can search for them by typing into the little autocomplete box. How is even your phone solving this problem? Well, let's consider a simple approach. I'm going to look at the first page and look for someone on the phone book. Suppose that person's name is Mike Smith, last name starting with S. Let me go ahead and look down. He's not here. Let me turn the page. Let me turn the page. Let me turn the page. This is an algorithm. It's a step-by-step process for solving a problem, finding Mike Smith. Is this algorithm correct, would you say? Yeah, I mean, it's pretty slow. It's pretty stupid in that it's going to take, my God, forever, like hundreds of page turns to find Mike Smith. But if he's there, I will find him according to this step-by-step approach. What if I speed things up a bit just because it's tedious otherwise? So I do 2, 4, 6, 8, 10, 12, 14, 16, and so forth. Is that algorithm faster? Absolutely. Literally twice as fast. Is it correct? No. Why? Yeah, we might skip them. I might get unlucky, and eventually I might get to like the S's, but darn it if Mike wasn't in between two pages as I turn them at once. So it's not a fatal flaw. That algorithm I could fix by just saying, if you hit the T section or maybe SN instead of SM, just back up one or so pages just to fix that bug or mistake, so to speak. But it at least is twice as fast. But if this phone book has like 1,000-something pages, it's still going to take me maybe like 500 pairwise turns just to find Mike Smith. That's a while just to look someone up. But most of us, if you've used this technology, instead did what back in the day? You know, go like roughly to the middle, right? If there aren't little letters on the side of which to cheat. So go roughly into the middle. I'm in the M section. Now the M's, of course, mean that Mike is not this way, which would be the A's. He's probably this way toward the Z's because S, of course, is between the M and the Z. So at this point, I can literally tear the problem in half, throw half of the problem away very dramatically and unnecessarily, making the point that we've now gone from 1,000 some odd pages to what, 500. And I can do it again. I went a little too far. I'm now in the T section, so I can tear the problem in half again, throw that half away, and now I'm down to from 1,000 to 500 to 250 pages only after just 2 steps in this step-by-step process. And if I repeat this again and again and again, hopefully I'll be left ultimately with, say, just 1 page on which Mike Smith either is or is not, and I can call him or quit. So that algorithm would get me to the solution so much faster, and we can appreciate this even if we just look at some of the numbers ultimately as follows. So if I start with, say, 1,024 pages total in the phone book, and I'm looking for Mike Smith, and I divide and conquer this problem, splitting the problem in half and in half and in half, I go to 512, I go to 256, 128, 64, 32, 16, 8, 4, 2, and 1. After just 10 steps, I have found Mike Smith's page. By contrast, that first algorithm, where I just did one page at a time, how many steps maybe might it have taken me to find Mike Smith? Yeah, like 700, 800, roughly where the S's might be. So in the worst case, 1,000 pages if I look through the whole thing. The second algorithm, maybe 500 pages because I'm going twice at a time. But my God, 10 steps with this algorithm here. And odds are that would be the algorithm most of us in this room would reach for by default, which is to say that a lot of problem solving really, as we'll find, is just about harnessing your existing intuition and comfort with ideas that now you just need to translate in such a way that machines and other humans can understand. So how might we just think about how much better that algorithm is? Well, consider this first line here. On this y-axis or vertical axis, let me describe this as the time to solve some problem. And on the horizontal or x-axis, the size of the problem. So the number of pages in the phone book would get bigger as you go to the right. And the number of seconds or page turns required would go up along the y-axis here. So that first algorithm, depicted here in red, suggests like a one-to-one relationship between the number of pages in the book and the number of seconds to find someone. So you have this straight line, a slope of 1 over 1, if you will. And so if we consider the second algorithm is also going to be a straight line, but that straight line is going to be lower on the graph. Why? Because for any size problem, it's going to take me half as much time to search that phone book, because of course I'm going 2 pages at a time. So if we see this, for instance, if this dashed line represents some number of pages in the phone book, maybe 1,024, well, you can see that it might take this many seconds or page turns to actually find Mike Smith with that second algorithm. But in the first algorithm, that same number of pages would take way more time to solve, literally twice as much time in this case. Well, what about the third algorithm? Well, even if your memory of what a logarithm is a little hazy, it just describes a fundamentally different shape. The green line describes that third and final algorithm, whereby you divided the problem not 1 page at a time or 2 pages at a time, but 50%. Again and again and again. You halved it again, again, and again. And notice that as the number of pages in the phone book gets really large, you barely make an impact on how much time it takes to solve that problem. For instance, if Cambridge and Alston, 2 towns here in Massachusetts, merge next year and their phone books become one phone book that's twice as big, so not 1,000 pages each, but 2,000 pages total, how many more steps might it take us to find Mike Smith in next year's phone book if it's got 2,000 pages instead of 1,000? Just one more step. But the first 2 algorithms, that's another 1,000 steps maybe, or another 500. These are fundamentally big differences in efficiency.
Okay. I hope you enjoyed that, or that made a little bit of sense. Any thoughts?
So
Does it only works on binary trees? You can't use it on just any tree structure, right?
You can. That's a good question. You can only use it on a sorted data structure. Like an array that's sorted, or a binary search tree, which is sorted. Mm-hmm. Other thoughts and questions? Jonathan?
So in order for us to actually make a binary search usable, we would have to sort the array before doing anything else first, right?
That's correct. The array will need to be sorted, or you will need to sort it. Yeah. Mm-hmm. So let's do an experiment here that I saw. There is a book that I wanted to recommend. Let me recommend it first. It's called Grokking Algorithms. You might have heard of it. It's not as big as not as big. It's more here. Actually, let me just share my screen and you'll decide. I really like it because it has some drawings. So it's called Grokking Algorithms, and it's very nicely illustrated. It is rather pricey, print or the ebook version. But basically, it shows like with a lot of graphics, a lot of these algorithms and their explanation on binary search and many other like trees. They explain trees, the trees data structure is very digestible, and like, yeah, I think the illustrations for me really, make this book worth it. If you're unsure, and especially because it covers a lot. Actually, let's take a quick look inside. If this let us do that. Yeah, for instance, it works over sorting algorithms with, as I say, a lot of graphics. Let's see, is there breadth first? I don't think they have binary search here in the demo section. But it explains, as you can see, yeah, recursion, and yeah, they highly recommend it. Okay, so from here, I got an idea of a binary search we could do, and that's this question.
Pupils
Yep.
in the waiting room.
Oh, thank you.
I also shared the PDF to this book on the
Okay.
top.
Cool.
Thank you, Suzette.
So from here, I got an idea. Well, let's see how it goes. So let's say this is, the binary search algorithm experimenting a little bit. Let's say I'm gonna pick a number from 1 to 100, and I want you to, and I'm gonna ask you some questions. So I'm gonna ask you to guess a number from 1 to 100. I have picked my number. I am the only one that knows the number that I picked. Actually, maybe not the only one. I have to change it because I typed it in the board. And I forgot that you have access to the board. Okay. And so the question is, I have my number. The question is, how many questions can you ask me to make sure that you guess the number? Let's say, and you can ask me a question at a time. What is the maximum number of questions that you could ask me? And what do you think? What is the maximum? Maybe what is the minimum number of questions you can ask me to find out the number? And if you make a guess, I'll give you an answer. So, and thinking of binary search, how would you do that?
Is it above or below 50?
It's above 50.
Is it even or odd?
Okay, is even.
Is it above 50 but less than 75?
Less than 75? No.
So it's above 75 and less than 100.
Okay, what are the numbers in between 75 and 100, right? So from there, what if you repeat the algorithm that you were trying to follow?
Is it above or below 87?
It's below 87. Is anyone taking note?
Is it above or below
80, like 81.
It's above 80.
Above 80. So it's above 80. Is it above or below 83?
Is it?
Right?
Is it 100?
No, it's not 100.
Is it?
Yeah.
Is it 84?
It's greater than 84.
Then 86.
That's correct. Bingo. Got it. I think we didn't follow the algorithm exactly, but we saw that we didn't have to go through all of them to find out what the number was. It was 86, the number that I had taken note. And I want to highlight what Jonathan did, which is he went for half and tried to get rid of half of, he did get rid of half of the problem there by asking if it was less than or greater than 50. And then from there, we went to 75, which is roughly half of 50. And then from 75, I said it was greater than 75. And then we went for roughly half of the middle point between 75 and 100, which, what would be the middle point? I think the number that was there was 87. And so on. And we just repeat that step until you find it. Roughly, how many steps would that be? Using binary search. Using binary search to find a number between 0 and 100, between 1 and 100. So how many questions can you ask me?
At max 10?
At max 10? What was that, Owen?
Log of 100?
Log 2 of 100, yes, that's correct. What would, so actually let's do some, let me share my screen here. Screen share. Oh, also, I just got a message from Ben. He said his internet is down. He apologizes, but he will try to join as soon as he's back up. But he doesn't know if he will be back up. So just letting you guys know. Ben is having some issues with his internet. Cool. So let me share screen here. The first number that I was thinking about was 87, and then I realized that oops, why isn't this changing? So let's do, if we end reducing the numbers, we'll do, we started with 100. From 100 we went to 50. From 50 we went to 25 numbers. 25 numbers.
12 and a half.
12 and a half. Let's say 13. Actually, let's say 13 to include that remaining one. And then let's say 7. Oh, am I doing this correctly? Yeah. 7. Let's say 4, 2, 1. How many steps was that? 1, 2, 3, 4, 5, 6, 7, 8 steps. And as we saw in the video, if it's now 200, how many steps? If it's now double, so 100 took us about 8 steps.
So it'll be 9 steps.
It'll be 9.
It'll be 9 steps. And this goes roughly like that. And this sort of this math that we're kind of doing here is expressed by the log is it function? I don't remember what it is the word called.
The function.
Log function.
Yeah.
Cool. Thank you for that. But let's actually verify, because I actually don't know if log2 is log2 of 108.
6.6.
6.6. Okay. That's close. Trying to think. Oh yeah, I should have picked an easier number than 100. But for instance, if we have 1,200 and 1,024, if we have a search list of 1,024 elements, it will take us 10 steps to find the element we're looking for. And hopefully we can actually do some, we can actually have the algorithm and run it through some examples and see, and count actually the number of steps that we end up doing. Okay, so the key in binary search, just conceptually, is getting rid of half of the problem as you're going, and you can only do that on a sorted input, basically. Okay. And does it make sense why that that compared to linear search is so much better? Does that make sense? Give me a thumbs up if that makes sense to you. Okay, I see some people missing. Joanne or Hugo, what can I explain up again or more clearly? So if we have a list, if we have an array of 1,024 elements, so basically we have two ways. One is using linear search and binary search to find the element. How many steps would linear search take? Or how many comparisons do we have to do in linear search? Pupil or Joanne?
Oh, sorry.
I think it's probably going to be more. I want to say twice as much, but.
No. You're saying like 20? 20 steps in linear search?
I'm not really sure.
Okay, that's fair. What about you, Hugo? In binary search, we take 10. We only need to make 10 comparisons. In linear search, how many comparisons do we need to make? But first of all, I guess, like, what is linear search?
Well, wouldn't linear search just be like each like element like one by one?
Each element one by one. Okay, so how, if we have 1,024 elements, how many comparisons do we need to make?
Well, 1,024, like one for each one.
That's correct. That's correct. So that's a big difference from 10 to 1,000, and that just, that gap just goes in opposite directions. In fact, if we look at Bigo cheat sheet, we can see here, we can see O of n squared, right? We can see how it goes up. That is considered a bad or horrible, as this website puts it, a horrible time or space complexity. And we see logarithmic here going, this is actually, it's not, the graph that he showed was a bit better, where it shows like a curve, and the curve never really flattens. The curve never really flattens, just like in the way that this curve of the n square, it never really goes straight. It never becomes like fully horizontal, not horizontal, vertical, and so on. But it's the similar curve for log n. it never goes completely horizontal. But well, I guess what I wanted to say is that we can see how when we have this algorithm, the linear search on O of n, and the algorithm on log n, those two lines will be separating all the time. Like the log n staying almost flat, never fully flat, but almost flat, and the linear always going straight, so diagonally up in a way. And also something that like in the mathy sort of side of this, the logarithmic function is like the opposite of the exponentiation, or the what's that operation called?
Exponential.
Exponential, or basically like logarithmic is the opposite of elevating something to the power of elevating a number to the power of something else. Let's see, log explain. We're going to see something small. I'm sure this one might actually be a good one. So let's see this example. Am I sharing my screen? Yeah. I'll put this here. I'll put this like here. So like log 2 of 8 is basically saying how many times can we multiply 2? Wait, no, how many times can we multiply 2, or the base of the log, and how many times can we multiply that to give us 8, basically, and that is 3. And the opposite will be here. Let's put this here. So we have log 2 of 8 is equal to 3. As we see here in this example, how many times can we multiply 2 to get to 8? And the opposite of that will be, the opposite of that will be 2 to the power of 3, which is 8. Right? And here is like, this is the same number, kind of. And this is this number. And this is this number. I don't know if that makes sense. I don't think I'm explaining it very well, but I wanted you to keep in mind that logarithmic is the opposite of the exponentiation, or the elevating a number to the power of some other number. And it's funny. It's interesting. What is interesting is that if we have the graph, a runtime that is exponential goes like this, and a runtime that is logarithmic goes like this. So that's also something that I thought was, that sort of makes sense with this, how log is the opposite of exponentiation. Like this could be of n squared, and this could be log n, log of n, right? Where the graph itself is also like the opposite in a way. Okay. So whenever you think of log, also keep in mind like getting rid of half of the problem. And here this this base, when we're talking about logarithmic time in programming, we're always talking about log base 2. So just keep that in mind. And some people don't even write the 2. You will see that in the big shape, in this spreadsheet, they don't write the 2 because it's assumed that that's what they mean. I'm not exactly sure like what the reason exactly behind that, but just keep that in mind. Okay. So then let me take a look at here. What else do we want to do? Okay, so cool. Let's jump into like actually implementing this. Actually implementing it. So let's describe it first here visually, and then we can write the code. Should have not done that. So let's say, let me take this space here. So let's say we have this array. Actually, where did it go? Let's say we have this array, 1, 3, 5, 7, and 9. And we wanna do binary search on it. So what we'll do is we will have 2 indices. I'm gonna call high and low. I'm gonna make those maybe green. I'm gonna call low, it's pointing to this, and high is pointing to this. Okay. So we're gonna have 2 indices, and this indices is gonna help us narrow down what part of the list is the one that we're looking, or what half of the list is the one that we're looking at. And then we're gonna have a middle point. I'm gonna put the middle on a different color. Just call it mid for now.
A quick sidebar question. If we run a like dot sort on this, does that undo all of the the bonus like the good time complexity of this? Because it's a like a loop under the hood kind of thing.
That's correct. That's a good observation. Like if you're giving an array and it's not sorted, or maybe you didn't ask if it was sorted and you sorted, what's the time complexity of sorting an array?
That is linear, because it's going to take the length. It's O of n, because n being the length of the array.
Sorting is not linear time. Any other thoughts from one of the peers?
Is it n log n?
That's correct. N log n. So it's n log n. It's n times log of n. And I think we can't get into like why exactly, but let me take a look at here. This. See, for instance, merge sort. Merge sort is n log n, right, in sorting. Even in the worst case, merge sort is n log n. It's a bit difficult for that, but we saw that log of n is like something with halves, something related to halves. And this is n log n, because I don't know if you remember merge sort, but in merge sort, we divide the array in halves, and then we merge them. Actually, let's just go there for a second. Merge. Let's go here. Merge sort, and let's just see this. So this is basically the visualization of merge sort, and at each step, we're splitting in half, and we split in half, and then we merge them, and roughly that is, we're doing that step roughly n times, which then gives it an n log n. I mean, that's the best time you can get on sorting an array. I think I had read somewhere that there was like, if you can find an algorithm that's able to sort an array in less than n log n, you probably win the Nobel Prize for that. And yeah, so let's go back here. So n log n, basically n times you can think of it, you know that binary search is log n, so n times search. I was just thinking another sort of way in which you could sort an array is, imagine if you have a binary search tree that has an insert method that you insert an element, and the binary search will insert it in the right place, right? That's actually an example. Imagine we have a binary search tree like this one, we have here. Let's say this tree starts empty. The tree starts empty, and then you insert 1 into it, and the tree will put 1. It will put 1 first at the root. It will put 1 at the root, and then you insert 3. It will put 3 on the right of 1. So actually, I'm not sure if this will end up well, but let's try it anyway. So let's say we have a binary search tree, and we have this array. So what the sort we will do, I think it has a name somewhere. I think it's probably tree sort from the ones here. We have, tree sort. Now in the worst case, that could be of n squared, but I think it serves to demonstrate the point. Basically, let's say we have a binary search tree, and we have an array. Oh, but this array is already sorted. You know what? Never mind. Because I think the example that I wanted to give is, we can go down a rabbit hole there. But basically, imagine you have a binary search tree and you have an array that's not sorted. And what you do is you iterate over the array and you tell the binary search tree, insert this into the binary search tree. And the binary search tree, because it's coded in a way that will preserve the binary search tree properties, which is everything to the left less than, everything to the right greater than or equal to. Then at the end, you will end up with a binary tree that has that is sorted, a binary search tree that's sorted, right? And the number of time, or the time complexity of that, we can say is, well, we needed to loop over the array, so that's n. And then the binary search tree had to find out where in the tree that element should go to keep the binary search tree properties. For the tree to look at where each number should go in the tree when you're inserting, that will be a log of n operation. And that's where really like n log n comes from. It's just depending on the sorting algorithm, it's a bit difficult to see. But if we think of it as, you have an array that's unsorted and you have a tree, binary search tree, then if you insert all the elements from the array into the binary search tree, then by the end, the binary search tree will be sorted. It's a binary search tree. And then I guess from the binary search tree, you could put it back into an array, but that will be let's say that's not necessary. But basically that ends up being n iterations to loop over every element in the array. And the binary search looking at where each element will be, that's a log of n operation, because we were talking about it here. To search an element in the tree, we're getting rid of half of the problem every time. To search where to insert an element in the tree, it will be the same operation, like searching where it will go. Let's see. Wait, I think I saw somebody coming in. Okay, yeah. Okay, so we have this array. We're gonna have a low and a high and a min, and let's do. And what we'll do is, let's say we're searching for. Let's search. Is this the? What is? Let's say we're searching for 3. Actually, this is a bit hard to see it here, but let's do it. Let's say we're searching for 3. And what we will do is we'll check if the array at midpoint is equal to 3. If it's equal to 3, then we found it. If not, we're gonna check if the element, let's say we're searching for 3. Searching for 3. If not, what we will do, actually, you tell me, what should we do? If, let's say, let's call it actually guess. Let's say guess. I don't know why I'm writing like sideways. Let's say guess is equal to array at mid. And then we check if guess is equal 3. If true, then found it. If not, we want to check, we want to do something. We want to check if it's less than or greater than. So if guess is greater than 3, what should we do? What is, in this case, our guess is 5 at the moment. So if guess is 5 and 5 is greater than 3, what should we do to reduce this problem to half?
You should go to the right.
Yeah,
We
the
should
little
go
pointer has to move.
So we should go to the right. That will be this area, right? But the 3 is not in that area. Brianna, I think you said something.
3 is okay. So if the guess is 3, then we found it. Really, 3 is the number that we're looking for, but we guessed 5, right?
That's correct.
Okay, so that means if our guess, which is 5, is greater than 3, so we should be moving the high pointer to the current mid.
That's correct. That's correct. We should move the high pointer to the current mid so that we search this area. So let me erase this here. And what we will do is move this high. We will move it to be here. So let me move this first. So we'll move 5 here. And then, okay, so actually let's do this here. So what should this be equal to then here? If we do, let's say, actually, yeah, let's do this. Let's call this number the target, so that we don't use like the numbers here explicitly. This is a target. So then what we will do is we make high equal to our middle. Right, that's what we did. Does that make sense there? Okay. And we need to recalculate the middle. Any ideas on how we could recalculate the middle so that now the middle points to this?
Let it equal to previous mid minus 1.
To the previous mid minus 1. Okay, that would work for this example actually, but it will work for this example because this is a small input.
Set do you have set high to be? Wait.
Right, I think we should have
pointer?
started there. I guess what is low, what is high, and what is mid. If we go back to where we started. Where should we start?
So low is 1, high is 9, mid is 5. Or we're using index.
How do you calculate the middle?
Yeah, I think it would be index 0 for low. High would be array.length minus 1. Or is it no, array.length? Or is it, wait, hold on, I'm getting turned around.
That's correct, minus 1.
Yeah, minus 1, because yeah, we're looking for the index, not the length of the array.
And how do we calculate the middle point?
That would be array.length minus 1. Oh wait, no. Yeah, array.length minus 1 divided by 2.
So let's call it high minus divided by 2.
Wouldn't it?
Should we use a math.floor for that too?
Oh yeah, we're gonna need to do math.floor for that.
Yeah.
Shouldn't it?
High, low plus 1.
Yeah. Oh, I was gonna say high plus low divided by 2, and then you can math out for that.
Yeah.
And why is that? Wait, am I spelling high correctly?
Yes.
Yeah.
High's one, or is it like weird? But that's actually how you spell it.
You're missing that.
Because your high and your low is eventually going to change, and your high is eventually going to change. So you need to add. It's really like the two of them because you want the middle of where you're starting and where you're ending, not just the middle. Higher, right?
Okay. Does that make sense for everyone? Give me a thumbs up if that makes sense. I think this is the part that it's a bit hard. I know that it was hard for me for like, why don't I just do like array length divided by 2? And as Peter mentioned, because high will change here, where we put the middle here and we put high here, well, how do we calculate then the middle to give us 1, right? This is then what we could do. And we should floor this. So I'm just gonna call it like floor. Flooring all of this. Okay. And basically, then we have the middle point. Let me get rid of this. Put this like here. And then how? So we have a way to calculate the middle. There is also this also always throws me off a little bit where we make the mid plus 1. The high, we make the new high plus 1 or minus 1. We'll get to that because I don't remember exactly. But basically, what is the other case we have? Let's actually say here, like if this, and we found it. This, oops. If this, then that. Else, what do we do in the other case? In the first case, we increased the high. Well, we made the high the mid. Join.
The low is gonna become the mid.
Low is gonna become the mid. And there's +1 and -1 here that I don't remember exactly why we need it. Let me double check just to make sure that I'm telling you the right thing. Yeah, this is correct. So min -1 becomes a new high. I think it's because, let's see.
It moves the bounds down, so you ignore the previous mid.
Could you explain that a little bit here?
So it moves the so 5 was a mid before.
Mm-hmm.
Realize it's not the right one, so we don't want to count 5 anymore. So you want to set the mid to be the high to be mid -1. So take 5 out of consideration for the newest search.
I see. Thank you. That makes a lot of sense. Did that make sense for everyone else? So we already checked the mid, so we don't need to check that anymore on the first try. So what we do is just move the high to be the mid -1. And I guess the opposite is true for the other one. When we have like when we have, let's say we were looking for 7, then the low. We already checked the 5. It's not the 5, so we don't need to check that one anymore. We can just make the low in here. I guess in this case, what should this give us? If we have high 4, what would be the middle point? High 4 plus the low 3 divided by 2. 7 divided by 2, and then that's 4. Would that be 3? No. 3.
3.5.
Right. So 3.5, and let's say we floor it, and then so our midpoint. This will be an instance where our midpoint and our low point will be at the same point, basically something like this. So, which can happen, and that's basically when we find that is the element that we're looking for. Okay. So, any questions or thoughts in this? Okay. Let's take a 5-minute break, and then let's write this in JavaScript. Let's see it run, and let's do some exercises. So it's 8:12, 17 minutes. Yeah. Okay. Give me a thumbs up once you're back with us. Cool, thank you. Okay. Is everyone still seeing my screen, right?
Yep,
Yeah.
you're coming in clear.
Cool, thank you. There's one thing that we also need to address before we write it, which is when do we stop? When do we stop going? When do we stop our? How many times do we have to do this where we move low or high in the array? Any thoughts on that? Or what if here? What if we were looking for? What if we were looking for 8? What if we were looking for 8? We will go. The low will become mid plus 1, which will come here. And the mid will become, as we did the calculation, the mid will become the same as low. Okay, and we check the mid. We check if 7 is equal to 8. It is not. Is 8 the guess greater than the target? It is. So we make the high equal mid minus 1. What's going to happen there?
The high would be less than what the current low or mid is, and we can't. That doesn't work.
Right, that's correct. The high will become this one here, which is my crooked arrows prevent me from doing. But basically, the high will overpass the low, right? And then is there where we know we need to stop, basically. We will stop whenever the high stops being greater than the low, basically. And we'll hopefully this in the code that will make more sense. Okay, so let's take. Let me create a repo here. I actually have one here. Let's see. Oh, let's actually just use this one. Also, let me share. I think I forgot to share the lesson again here. I updated it, and let me share it here so you can have it. Binary search, JavaScript. So to the chat. The code we're gonna write is there. This just the lesson just talks about what we just talked about. Let me close some of this stuff. Okay. And then the REPL. So I'm gonna share this REPL here. Copy. And I'm gonna put it here in the chat as well. Guys, all this I'm gonna be sharing later on in the the online resources channel. Okay, so I put the REPL in the chat. And that is this that we have here. Close this here, make this smaller, make the text bigger. Okay. So here there's some code for binary tree, binary search tree, but we can ignore that. What we're gonna write is our code here. I'm gonna call this target. And this is the array that we had. Basically, this is the same stuff that you will do like in whiteboarding. We solved the problem here. We talked about it here in these drawings first, and we already know what low and high should be and what mid should be. Anyone that's in the repo want to type that here? Yeah. See, Joey, you type the low, the high. You type the high. Brianna, you type the mid. Okay, cool, thank you. That is correct. Nice, 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 nice. Cool. Thank you. Okay. Cool. I don't know why this is giving me these squiggly lines here. Oh, this for some reason it's trying to interpret TypeScript, I guess. Anyway, this looks good. Great. So we have our high and low, and then we said we will need to loop for, or we want to repeat this operation that we're doing as long as high is less than low, less or equal to low. So for that, we'll just implement a while loop that says, as long as high is greater than or equal to low, do the following. And then we just need to remember the conditions. Let's have a guess. We'll have that guess equal array at mid. Say if the guess triples equal the target. So for this, actually, let's return the index at which we found it. So if we're searching for 3 in this array, we'll return 1 because the element was found at index 1. If the element is not found, we can return null, or we could also return -1. Let's return -1 if it was not found. So if the guess matches the target exactly, we want to return the index at which we found it, which is mid. Else if what we would say, the guess is greater than the target. What is it that we want to do here? If the guess is greater than the target,
we need to move the low up to where the mid is.
So we want to do low equal mid plus 1. Wait, actually, I always get confused.
The other way, it's the other. If the guess is greater than the target, it's that we're moving the high.
Remove the high, yeah. Remove the high to the mid -1. I'm not sure if let's put the curly brackets because it looks like we are without the curly brackets.
We want to calculate the mid in the while loop.
Oh, that's a really good point. Yes. Runil brought up the point that the mid, let's calculate the mid in the while loop so that it calculates the mid every single time. Otherwise, the mid will stay in the same value, or we'll have to recalculate it here. Thank you for that. Let's move the mid there. Else, we put the low equal to mid plus 1. And we have we close the while, close the function, otherwise return -1, right? That means that we didn't find it. Also, if you go to the lesson, which I had annotated here with some comments, basically. And basically, there's another way. This I took from the Grokking algorithms. These comments basically. Well, we haven't narrowed the list down to one element. Basically, that's what the while is explaining. And we can see that even here, I did it the opposite. I say, well, as long as low is less than or equal to high. I think that I did the opposite here, where it said as long as high is greater than or equal to low. But that's the two sides of the same coin. We'll calculate the middle point, check if that's the element. If so, we found it. Otherwise, that means that the guess was too, if the guess is greater than the value, that means that the guess was too high. We need to lower the height to the middle point. If the guess was too low, we raise the low to the middle point +1, basically. Let's make sure that that's the same thing what we have here. Guess too high, lower, high, high to middle. Right, and otherwise the guess was too low. Let's increase low to the middle point. Okay, questions or thoughts about this? Is it making sense so far? Okay. So let's run it. Let's see what we get. Run this. Oh, the binaries are still running. We get 1 on -1. That's correct. We should try with some more numbers. Let's also console log here. Console log. Actually, instead of console log, let's say let steps equal 0. And on each iteration, we can console log. We can. I just want to count how many steps we're doing. And then at the end here, just console log steps. I have a spelling here. Cool. And as we saw when we do it manual by hand, we took only 2 steps to do that. Only 2 comparisons that we needed to do. If we have, actually, before we go there, questions, thoughts, comments on this. This is binary search, and for instance, like if you need to, if you're taking the DSA reassessment, the binary search problems that are there, they're basically this. This is the algorithm that you will implement. The only thing that will change is like the equality check, basically, like what is it exactly that we're looking for. And I have some examples that problems that we can do for that as well. That is just not with numbers. That we can do binary search on anything. It doesn't have to be like a number. It could be strings. It could be truthy values, and etc. As long as that array is sorted in a way, we can do binary search. Okay. Any questions or thoughts? Okay. I'm thinking it will be cool to see this with a large input and see what we get. What if we do this? But I guess I'm not sure where. Let's see. What if we do new array? Actually, I think we need to make it here. Let's call it that A equal. Let's fill it. Let's fill that array. Does anyone remember the array fill JavaScript method?
Jonathan should know.
Jonathan?
I used that one time.
I guess I was thinking in Python there's a way to fill out an array easier. I'm not sure if that's also.
I think array.fill gives you like the number of indices that you want, but I think that they're undefined.
That's correct. Actually, and I forgot to do that here. Let's try with 10. So we do that, and then we fill it. Can we pass? Oh, it would be great if we could pass. Oh, you know what? Just with map. With map, we can do it. Let's do map. And what we'll do is we have an array of 100 elements. And what I want to do is fill it out with numbers 0 to 100. So here we'll get the element, and we'll get the index here. And I'm just going to return the index here. Return I, which would actually not be necessary if we use implicit return, just like this. Let's console log I just to make sure. A, I mean. Yeah. Oh, it says 100 empty elements. I thought this should be maybe. Does this make any sense for anyone? I want this to fill out the array. So I guess what if I do? Oh, right. It's because map mutates the array or not? Does map mutate the original array?
Returns a new array.
Returns a new array. So then and why do we do this? That still doesn't work. Okay, let's say let A equal A.map. Oh, actually, this is interesting. See what we get here. Now I have some extra parentheses. I guess I'm overcomplicating this. I guess we'll need to just do it with who was that? O'Neill?
No.
Cool.
Sorry, no, I did it quick. I apologize.
Oh, got it. Cool. Thank you. So let's see how many steps does it take to do 10 elements. It took seven steps, right? Yeah, it took 7 steps. Wait, what is this? Oh, I see. This is still nums. I'm doing it wrong. Oops.
You forgot the S. 79 in nums.
Thank you. It took 5 steps there. I guess it will depend on the number of steps. But we'll see that what I wanted to demonstrate really is that that is going to be very low, even when we duplicate and when we actually have a really large array. But let's see. Zero is less than. Let's try with 1,000. We see that even with 1,000 elements, it only took 10 steps. Let's add another 0. 11 steps. And so on. We can see that like I'm increasing this number considerably, and we do console.log a.length. Just to make sure that that's not, yeah, that's not empty, not just empty. Oh, that is actually quite interesting because I don't have the curly brackets. Oh, actually, never mind. Yeah. Okay, I guess like the point I wanted to make is that we're increasing the number, but the number of steps is very increasing rather slow, and that is basically the logarithmic function, like literally. Okay. Other questions or thoughts on this? Okay, cool. I want us to look at, actually, let me give you this, see, like, as an exercise. This algorithm, binary search, can be implemented recursively. Because basically, what we can do is, we have binary search, we check if the middle is the point, is the target. If not, we could just call the same function, but on the left, right, or on the right, on the left side or on the right side. But to make it recursive, we'll need to make some changes. I want to give us some time to attempt that. Try to make this algorithm binary search, but recursively. I'm gonna go ahead and just binary search rec. Let's do, actually, let's do 7 minutes. If not, just think about it, maybe write some comments. Start thinking about what will be your base case. What is your recursive call, and what are the means in which you're gonna reach that base case. So individually, let's try to make it recursively. Let's see, then discuss how far we got. Okay. Any ideas on how to make binary search recursively on the array? Anything that came to mind?
Would we have to include the low and high as arguments for the function along with the array of the target?
That's a very good observation, yes. We will need to have the array here, the target, the high and low. So let's put low and high. We'll need to use those for the recursive call. So, and actually there is a recursive approach here in the lesson. I want us to try a different one, and then maybe we can compare it to this one. And then we can talk about the differences. But yeah, let's try this. Okay. Any other thoughts?
Wouldn't it just be to take out the while loop and put the recursive call in the if statements?
That's correct. The if statements will be okay. Let's copy this. Oh, also, I don't know who has the text highlighted. If you could stop highlighting it, it will be nice. In the REPL. Thank you. This button doesn't work out of format. Oh, it does work. It's just a little slow. Okay, and we said that we'll return. Oh, actually, this is interesting. This is going to be interesting. What did we return? But yeah, the recursive calls will go here, where if the guess is greater than the target, what we want to do is binary search recursively. And we said that we want to search on the left side, so we lower the high. What we'll do that is we'll pass the target, the array, we'll pass the same target. We'll pass the same low. And the high will now be equal to the mid minus 1. Mid minus 1. And we also need let middle. Actually, let me just copy this line from here.
Would the return be mid minus or plus the recursive call?
That's correct. Let's do mid. Mid still the same. Let's say guess is still the same, which is the array at mid. And in the other case, oops, the other case is the opposite, where the new low is mid plus 1, and the high stays. Sorry?
I said we need the base case.
Oh, we still need the base case, right? What will be the base case?
That would be if the high is greater than the low, then return -1.
Let's say, should it be greater than or equal to?
Yeah.
Return -1. But this is the same condition for a while loop. Our base case. Okay. Maybe this is it. But we would need this part here, where this basically will be return. We'll be return mid plus that. And same here, return mid plus whatever that index ends up being. Let's take a look. Actually, I haven't implemented it this way, and that's why I had the idea of this way as compared to the other one. Let's try this out. let's try. Do we have the original numbers? Let nums, or let's just do small input. Actually, I guess it doesn't really matter. Let's just do nums here. Let's also make sure that we do search recursive, run. Oh, maybe we got Stack Overflow problem. Maximum call stack size exceeded. We did get a Stack Overflow. Where do we have that? Target. Oh, right. You know where? So when we pass the recursive call needs the array, the target, the low, and the high. In the initial call, we never pass low. We never pass high. So I'm gonna need to pass those here. The low will start at 0, and the high will start at nums.length -1. All right, we need to pass those with the initial call. Let's run again. Oh, we got -1. But we should have gotten 2 for this one. Nums.length. Let me know if you spot the problem.
It's for 78, line 78, if high is less than low, less than or equal to. We have it greater than or equal to.
This one?
Yeah.
Right. Thank you very much. Yeah. Less than or equal to. Let's try again. We got 91 now. We're looking for, well, let me just make sure, array, target, then the low, then the high. The array, the target, then the low, then the high. Nums.length -1. And we're dealing with nums for now. Let's then also take a look at, I guess we could debug this in the debugger. Let's console log here, like mid, and have the mid there, and then the guess here. I think it's probably in this part that I messed up. Huh, this one is taking much more time. I guess. Let's see.
Is it because you have the mid plus in the returns on 86 and 88?
Yeah, that's what I'm suspecting. Yes.
I think that's when the guesses they're adding up, and I think that is equaling.
Oh, right. On which one? Which one?
You see where you have the mid plus and then the binary search and the returns? It's adding the guesses. 50, 25, 12, 6, 9. That equals 91.
That is correct. Wait, actually, no, I'm confused. I think there's one where I don't need to add. I think it's this one. Let me try this. Oh, plugin crash. I don't know what plugin crashed. But There's one where I don't need to add. I think that's what, from what I remember. Because we need to offset from the beginning. I mean, this is.
It's still, you still have it in both.
Oh, didn't save. Actually, I think it is here. This one. I think. Let's take a look. Yeah. So that is because when we go to the right, which is in this area, we need to account for what was the previous midpoint, and to that midpoint, add whatever the result of the index on the right side is, basically. On the left side, we don't need to add the midpoint. Because on the left side, the midpoint is already from the left side. I don't know if that makes sense. On the right side, we need to offset from the previous mean, from the previous midpoint. And then we see that we started at 49, and the guess is 50 because these are all just by one. And then we see that that's too low. Actually, I wonder if we could do it here. Actually, maybe not. Is this node? No. Let me try something. This is not the algorithm. Guess. No, I think it doesn't work. It won't work because we're in a browser. But we see that it's going to the left always. The left of 50, which is midpoint 49, then 25, then 12, and so on. It just goes all the way to the left. It goes all the way to the left, and that gives us here this. We just need to return whatever that gave us. When we go to the right, let's pick a number. Let's pick like 93. Oh, okay. Actually, I'm wrong. 390 now. Oh, wait. The midpoint. Oh. Yeah, no, so that means that I'm wrong here. I don't think we need to add on either side. Huh. I'm running out of ideas. On the right side, we see that the midpoint is 91. It has to be wait, why did it less than or equal to high? Mid 91. Here, let's do low. Okay, we see the initial range, the next after that. 88 and 99 is greater. 88 and 92. Wait, why did it go to 90, mid 93? The guess was 94, so it's going to be less than that. So it has to lower the high to the mid -1, which is 92. Okay, so actually here, this has to be, you see here where the high and the low are less or equal to, I think we need to do this less than. Because the next step, I think the next step is the one, if my intuition says correctly. Yeah, the next step was the one that where we will find the 93. I just had like, I picked an interesting number. But the next comparison where the mid is actually 92, that's where the 93 is actually found. What if, let's see, what if we, instead of this high less than, we do low less than or equal to high? Just trying to see if that also gives me the -1. Huh. No, wait, what am I saying? I'm saying this wrong. Okay. I'm not exactly sure I know how to explain the less than or equal to in the recursive approach. Any ideas? Like, I guess, yeah, this one is where the low, the high, and the mid are the exact same one. Are we doing anything wrong here in the math? No, the math looks good.
I have a question on
Yeah.
why is the high 99 if the highest number there is 100? Is it excluding 100?
It's because is length -1, and the length of this array is 100, right? And 100 -1 will give us 99. So it's right. The high is the last index of the array, and the last index of the array is 99.
Yeah, I guess I was just wondering why we're not including 100 at all.
I mean, we're not including because this is the index, the high index. This array does not have index 100 because it only has because indices start at 0. Does that make sense?
Yeah, it does.
Cool. Other questions or thoughts? Okay, and we'll see this one compared to the other one. How about, so what was the time complexity of this one? What was the time complexity of binary search in this one? We talked about?
Was it log
n? Log n, right? Log n. What's the time complexity of this one? Douglas.
Is it the same? Log of n?
Log of n is exactly the same because it's the exact same algorithm. Just implemented a bit recursively. Okay, what about the space complexity of this? What would you say? Anyone? Neil.
You say what was the space complexity?
Space complexity, yeah.
Would be for however many times it took to find
That will be space. That will be time complexity. Time complexity is like how many
because
times.
I would say like for well, it's added to a stack when it's
Wait,
recursive.
let's take a look at this one, the one that I have highlighted in the screen.
Oh, that one. Let's say it's
Or anyone wants to help, O'Neill? Space complexity. Time complexity, log of n. Space complexity. Is anything growing here?
it's
Well, what is your intuition? Even if you're wrong, what's that intuition?
It looks like we're just rewriting over the same handful of variables that we create.
Is it
That's correct.
constant? It's not
Who said constant? I think I still can't spot you. Is it was Brianna?
No, I think Suzette.
Yes, it's me.
Suzette?
I don't know if anybody can hear me.
Oh,
You're
I
going
see.
like in and out.
Okay. Yeah, Suzette, that's correct. Constant space. We're just rewriting the same variables. There is no array growing. There is no object growing. There is no linked list growing. Nothing is growing in space, taking up more space with relation to the array or the target. So it's constant time. Now that is different in the recursive one. And what is the space complexity in the recursive call? Any ideas?
Would this be linear?
Not linear. Less than linear. What's less than linear?
log of n.
Log of n. Log of n, right? So in these two algorithms have the exact same, the implementation of binary search, they're the exact same algorithm, they're binary search, but their implementation is different. One is recursive, the other one is iteratively, or iterative. The binary search iterative is log of n in time complexity, constant time in space complexity. The recursive approach is log of n in time complexity, log of n in space complexity. The space complexity is being taken up by the recursive call, or going into the call stack. Basically, like, it's interesting. Basically, here we can see the number of steps counted by these console logs here. That is the number of times that call got put into the call stack. This number of time that we have here, console log, 1, 2, 3, 4, 5, 6, 7. And we saw that log of 100 was 6.6, something like that. This number, we see 7 console logs, which is roughly log of 100, basically. So then we say log of n, where n is the length of the array. And if we here, let's do this one quickly. We're gonna put this, copy this. Put it on the desktop. Oh, this is interesting. VS Code keeps getting better. Yeah, okay, cool. Right. Okay, I guess oh, did we see? Yeah, let's do this. I think Python tutor. Anyone? Somebody has talked about this. Oh, I guess that I'm having trouble finding that one. Visualize. No. Python 2, right? Let's execute some JavaScript. Let's place this here. Visualize execution. Next. We can see, this is interesting now. We have the array here. I wanted to see, yeah, and basically this thing that we're going to see here, the calls in the call stack, with the low, high, mid, and guess. You can see that as I go, these are new executions that are being added to the call stack. And that is going to be 7. We're going to see 7 of those, basically. I think we finish here. Next. Last. I mean, I wanted to see the 7, but yeah, I hope you get the idea that there is 7 calls in the call stack on each recursive call. Okay, so that's this. This is then taking that space. Let's take a look at just to finish, or before we do some exercises. Let's take a look at this exercise. This is a recursive approach as well. Take a look at this. Take some time to analyze it, and see how it's different from the other one. Then let me know what pops to mind. Changing this.
It's this version is probably worse time complexity because of slice. Like it's easy.
That's
Like
a good observation.
I can wrap my brain around it easier because, like, right off the bat, you are defining a middle, then splitting it right away, so you have a left and a right, and then you're very clearly asking, like, is it the middle? If not, then look to the left, like do a recursive on the left, or do a recursive on the right, and then it just does the same. Like I like that. That feels clear to me. But I do think that's I'm not quite certain what Slice is doing under the hood, but that might add to our time a little bit more than the implementation we just built.
That is a good observation. I actually did not think about it beforehand, but definitely, I think it will be interesting. And there is a math for this, but I'm not sure I know it very well. Because on each call, Slice is just a little under the hood, basically, as you mentioned. And And here we're slicing from this 0 to the middle, and the right is everything from the middle to the end. And so I'm thinking. Actually, let's try to put it. Let's try to put it in paper. But actually, even before that, does this make sense as binary search? As as the idea of left and right, and this is this same algorithm. Okay, that's important. On time complexity, and actually the space complexity and time complexity of this both might be worst. Let's see if we can find out the let's see if we can find the math out. If it's not too complicated, I'm gonna take it here. I'm going to paste. Actually, not bad. Let me paste this here. Oops. It's a bit bigger. And for this array, let's see if we can actually see it for the array that we had initially. For the array that we had initially, which is 1, 2, 3, 5, and 7, and new variables, new arrays are getting created on each time we have because of the slice. The slice will create a new array. It will just create, so on the first iteration, we have 1, 3, 5, 7, and 9. And 2 arrays get created. One for, take a look, 0 to the middle, but not including the middle. So the first one will be 1, 3, 1 and 3, and the second one will be 5, 7, and 9. And then this gets split into 2, which is going to be 1 and 3. This gets split into 2. The middle here will be 5, and then 7 and 9. And then this 7 and 9 gets split into 7, an array with 7, and an array with 9. So the question here is then, how much extra space we're using? Yeah, this has to be much worse for sure. 1, 2, 1, 2, 3. Well, actually, something interesting though here is at each step of the, we start with 9 elements here. Not 9 elements, sorry. How many elements? 5 elements. And at each step of the recursion, we have 5 elements, right? Each step that we're dividing. It's just that we have 5, but it's just that they're in separate arrays. But it's still the same. Okay, so in terms of, and here just because this is the last one, we have just 2. But what I'm thinking is that then in the recursive steps, but on top of that, we're only doing this on the half that we're searching, right? We don't do it on the other half, only on the half that we're searching. So let's say we're searching for 5. Well, let's say we're searching for 7. Oh, 7 will be found here. So let's say we're searching for 9. So this never happens because that actually never actually happened. 7, we split. Yeah, if we do that, we end up having this, which is then 3 here, 3 and 2. I'm not sure I can see like the math going in here, but I'm thinking first of the space complexity actually. Because so I'm thinking if the space complexity is being reduced in half, when we first saw binary search, if the time complexity is being split in half at each step, right? Because we're splitting the array, we get rid of half of the array on each step. The same is happening here. The same is happening here. But I'm having trouble devising like the math for this. I'm sure there's sort of like a formula that would explain this, and I'm not sure if it's not n, but the question is if it's not n, then is it log of n in space complexity as well, plus the calls on the call stack. Actually, yeah, I think I'm unable to fully explain and devise this here. I think this will be a good question for taking to office hours with Aaron, or even with Ben Sussman as well. Any thoughts or ideas on this? Okay, so I'm gonna move on from here. But this is actually, if I find anything, I'll make sure to come back. I'll try to get in touch with Aaron. Actually, I'll remind everyone that Aaron is an engineer from Microsoft. He has DSA office hours. I'll be sharing the link later on. But this is something that I would love to go to him with because he's good at that. Okay, I think it was good that we did realize that there's some intuition that this will make it worst in time and space complexity. We can't tell how worst it will be, but I think it's definitely worse than the initial approach that we had. Okay, so the other thing that we wanted to do is, let me take a look at here. Yeah, so we saw the iterative implementation, the recursive implementation. Here's a question. Let's say, so we did binary search on an array. And slightly off topic, but I realized why the map was not working. It turns out that if you try to map over an empty array, map will not run. You can't map over an array that has 100 elements, but doesn't. The slots are empty. If we do let c equal new array, I make 100 of them, and I say c, they're not undefined. I'm not sure exactly what they are. If I try to key in them, I'll get undefined. But if I try to do c.map and I do element index, and let's say I just want to console log the element, map did not run. Did not run at all. We did not see 100 console logs. But if I fill it out with something first, that is, if I do, so C is still empty. Let's fill it out with ones. Then I will be able to do the math. And we see this return value is the return from the middle, but we see the 100. That's just something that I didn't remember. Empty items, map will not run on them. So like, good to know, little quirk in JavaScript. Okay, so what if then, here's a question. And this is actually taken from the DSA assessment that we had, where you had to find like the commits that were, you had to find the first commit that had a bug or that was bad, I think. But the idea is the same that we can implement with binary search, where if we have, let's say commits, we'll have, let's say, let's say true, false. Yeah, let's say this is an array of Booleans. And if I ask, can we do binary search on this, what would you say?
I'd say you can, because it seems to be sorted, because you have trues on one side and falses on the other.
That's correct, it's sorted. So here, if I ask you implement a function that, actually let's just try to do this. Implement a function that finds the index of the first false and don't use linear search. We talked about linear search. Let's use binary search. How would you go about doing that? Binary search to find the first false. And we can say like, we can say like, these are commits, and the true means a commit that has the bug. True is a commit that has the bug, and false are commits that do not have the bug. So earlier, these are later commits, and these are earlier commits. And true means the commit has the bug. So you want to find the first commit that does not have the bug.
I think it's a matter of you start at the middle and ask if the middle is, so you're looking for the first false. Okay, yep. So you'd ask, is that false? If not, you're going to need to ask if the adjacent index to middle to the right or left is false. If it is true to the right, then you need to move further, like you need to move further right to find the falses. So it's going to be, you're always going to be tracking right until you find false, and then you're going to move left until you find the first one.
Could you repeat that?
Forgive me, I'm trying to suss out the logic as I go. Yeah. Where you're going to start in the middle, and you're going to ask, is this true? If not, you're going to look to the index to the right, or the or one index higher, and ask, is this false?
So
if that,
yeah, let's do it here. You're going down the right path. Let me put it here.
Could you use, for that, could we do the same thing as before and use like the indices?
What do you mean? Yeah, we're gonna do binary search in this as well, so we will use the indices. So let's keep going with what Douglas was suggesting. So we have, we have our high and our lows and our mid. Actually, let me take them from here. Whoops. Oh, this is interesting. I just found out that when you copy and paste something, it actually gets redrawn. Okay. So in this case, where is our middle? Low stars here.
Index 3.
Index 3. Okay. 0, 0, 1, 2, 3. Okay. So we have here, and then we ask what question, Douglas?
Sorry to juggle my mute. So I guess I was asking, like, so I would think that when you find your middle, you're going to ask, is this true or false? If false, you need to look to the index to -1 from your index to see if that is also false. Because if it's also false, then you're too far to the right. You need to move to the left. But if it,
I'm not sure I'm not seeing the need for checking the neighbors though yet.
Okay.
So any other ideas? Maybe anyone else?
Well, for right now, since the mid is true and it's sorted where the false is to the right,
that's correct.
Then we should move the low to the current mid.
Okay.
And then recalculate the mid. So
right,
that would
we'll
be
recalculate the mid.
which one?
I guess we can do it.
3, 4, 5, index 5.
Index 5?
Yeah. Or to the right.
Here.
Yeah.
0, 1, 2, 3, 4, 5, you said. Is this correct?
3, 4, 5. You have it at 6.
That's why I always like to put them down here. Okay, and here we have false, but here we differently, or differently from what we had before, which is when we have an exact match, we know we found it. Here we find false, but that doesn't tell us whether it's the first one. Here's where we'll need what Douglas was suggesting, like check the neighbor, see if the next one is, or the previous one in this case, is true. If it's true, then that means that we found the first one false, right?
Can I suggest something?
Yeah, of course.
What if we keep doing what we're doing until the mid is the same as either high or low? Then the low would be a true, the high would be a false.
Okay. Actually, I like that idea. I think I see where you're going. So we said, okay, we saw a false, then that means we need to lower the high, right?
Yes.
So let's keep doing that. Yeah. We made the high. Wait, but we made the high is equal to the mid -1, right? According to what we had here in the code. Yeah, okay, so then actually that wouldn't work. But maybe then, maybe that's one operation where we can get rid of the -1. And that will actually be good because then that will put us here. Then we will recalculate, that will put us here. We'll recalculate the middle. Yeah, actually, I think that's a good example. We'll recalculate the middle, we'll have it here. Then what happens is, that's true, that's not the false we're looking for. This low will be moved onto, I guess this one we can have it here. Right? We'll have the low. Do we want to have, I guess it doesn't really matter in that case. We can have it here and then the mid will, the mid will be on the low or the high if we have it like this.
It would probably get recalculated to the same spot, to where the low is. And
to
then
the low is, yeah. Okay, so this one we do need to move it here.
Well, oh, maybe I'm missing something, but I would think the low gets moved to the mid, no?
To the mid here, but
Maybe
then the mid gets recalculated.
And but aren't you using math.floor?
Yeah, if
That's
we're using
correct.
floor, the low and the mid would be on the same.
So the mid will end up here.
Yeah.
Okay, and then maybe in the next iteration, then is that?
And then yeah, right when it would check if the mid is either equal to low or high after you calculate the new mid. So yeah, right here, it would see that it's the same as the low. And then depending on what we're looking for, like the first faulty, if we're looking for the first faulty commit, we'd return the low. If we're looking for the last healthy commit, we'd return the false.
Oh, yeah, that's actually a really good idea. Okay, let's try to write this in the 10 minutes we have left. Let me stop sharing and then try to write it. I'll also try to write my own. See if we can coincide.
No, we can't hear you.
Yeah. Nope. No audio coming out.
You should hear me now.
Now we can hear you.
Okay.
Coming in clear.
What was wrong?
Did you say something?
Yeah, I asked what was wrong with your audio.
I don't even know. I just that it wasn't working and you guys can hear me.
Okay.
Khadija, are you there?
Yeah.
Yeah. Give a few minutes after class.
Okay.
Anyone has anything? I'm actually still trying.
Trying to do what? What's going on?
We're doing an exercise.
Oh.
Okay, give me a thumbs up if you think you have something. Actually, give me a thumbs up if you don't have something. Okay. Okay. Yeah, it took me also some time. Let's take a look at something here. Let me screen share. So I actually had to rethink and like look at the drawing because it's confusing and it's not super easy. But basically I have this function find buggy commit. And it basically what we talked about here, like, and Joey's insight was really helpful for the high and the low. But what is interesting is that a lot of the small details in this function are different, but it's still binary search. It's still doing binary search as a whole. For instance, here I have as long as high is greater than the low. The same stuff here, and I have like if guess is false, I know that we could do if not guess as well, but for some reason I actually needed to see it explicitly. If guess is false, then we did what we did here, which was if guess was false, we moved low, we raised low, right? And that's what we have here. No, wait, sorry. You see, I still, my mind still gets confused. If the guess is false, if the guess is false, that means we might have gone too much to the right. So if the guess is false, that means we might have gone too much to the right. We lower the high to the midpoint, right, which is the guess. That's what we did here. Let's put this back if I can. What was our first one? Our first was this. Let's actually run through it with this. Midpoint will be 3. If I remember correctly, 7 divided by 2, 6, 3. So that's true. Then in our algorithm, if it's true, what we do is we raise the low to the middle plus 1. I raise the low from the middle plus 1. That goes here. And we recalculate the middle, which is going to be 7 plus 4, 11 divided by 2, 5. Is that correct?
Yes.
Okay, so that was false. We look at that false, and if we look back at our algorithm, it says, okay, if the guess is false, we might have gone too much to the right. We need to make sure. Let's put the high up until to the middle point. Note that I'm not doing -1 here as we were doing with the numbers. So I do high I take to the middle point. And here we will recalculate the middle point, which is 5 plus 4 divided by 2, that's 9, divided by 2 is 4. So the mid is the same as the low. That is now a true element. If we have a true element, that means that we might have gone too much to the left. And what we do is we raise the low to be equal to mid plus 1. Mid plus 1, which will be this guy here. And that basically is when we stop the algorithm, because that's what we have in our conditional. As long as high is greater than low, high is not greater than low anymore. I just return high, the element, which is this, will give us 5 in this scenario. And we can see as I run this, was finding that and index 5, if I add another one, now I moved one index, so now it's going to be index 6, and so on. Okay. And anyone had a different approach? I think it might be a different approach. It might be like the difference between the +1, not the +1, or the -1, either that and returning the low here. Maybe it might be different, but I hope this was helpful in understanding binary search in an array, and understanding binary search as the algorithm itself that can be applied to different things, not necessarily exactly numbers, and so on. Any final questions or thoughts? I'll make sure to share this, everything we wrote here in the resources channel. Okay, I think I just had a few reminders. Let me take a look here. Let me stop sharing. Yeah, okay. And I'll be sharing this also on the Slack channel. But a few reminders. July 14th, there's a virtual site visit to Attentive. I think it should be already in your calendars. If not, be on the lookout for that. There, as you know, I think there's a few of your classmates that applied to Attentive facilitated opportunity, and they're hiring. So you want to go to that site visit as well as a networking event as well. So July 14th, I actually did not catch the time. On July 16th, on the 23rd, 16th, 23rd, and 30th, there's going to be a 3-part software design workshop. I forgot to ask who's going to be leading that, but that sounds interesting. I know that I want to go to that. Different software. Oh, Carlo, thank you, Suzette. Yeah, I actually had that. Him was the first person that came to mind, but I was not sure. Yeah, so that should also be going out in your calendars as well. Make sure to read the Pursuit newsletter that comes every week. That has all that information as well, and more. As always, office hours with Jimmy are available on Thursdays. He keeps telling me the hours and I keep forgetting them. I think it's 1:30 to 4, if I remember correctly. If anyone knows, I would appreciate the reminder. But I think it's 1:30 to 4. You can message him on Slack to sign up. As well as remember office hours with Melon Lathy for professional skills. And the other one is office hours with Aaron. I'll be sharing the link on the Pursuit core workspace, the resources channel as well. The office hours with Aaron are for DSA. And I think I had already told you guys this, like he was doing office hours. He has been with Pursuit for a few years now. And I really liked his office hours because he was